Okay. So any questions about filling this table, choosing dates for June, and putting DOI on the table? Okay.
I have a question. Like,
yes.
Is there any time limit for the presentation? Like, it should be.
Yes. So I expect that most dates will have 4 speakers.
Mm-hmm.
I think our meetings should not last more than 90 minutes or 100 minutes, right? Let's say 100 minutes. That means 25 minutes per person. Okay. So you should plan on something like 20 minutes presentation and 5 minutes questions.
Mm-hmm.
We might have, I'm not sure if we'll have the full list of students. Right now, there are 33 registered. We have 9 meeting times 4, that's 36, so we have some spare there. If some people drop, we might either I'll give another presentation or we allow a little bit longer presentations, or the last meeting will be, we'll see. It's not that important. Other questions? All right. So
yeah, I have a question. I'm trying to understand exactly what are we supposed to present in regard to the paper? Are we supposed to just explain the whatever the paper is supposed to illustrate or say, or just
so the scope of this task is going to unravel itself over the 5 lectures that I'm giving, because I'm going to repeat it again and again. I'm going to do it today as well. But you will really fully understand exactly what I expect only at the last of my presentations, which is just before the Passover holiday. So we'll talk about this and ask questions, but basically I want you to give a good story of a unique paper, either because somebody really screwed up big time. It could be fraudulent, it can be just wrong, scientific methods, wrong conclusions, retractions, or I'm allowing also some exceptional good paper, but then you have to explain why they're so good. And I'm going to give some rules. I gave it, I'm going to give it again, how to look at papers and how to analyze papers. So at the end of the day, I really want you to pick up really good stories and tell us good stories. Okay? The main consideration, somebody is asking on the chat how to choose a paper. Well, that's part of the assignment. You all are very familiar with Google Scholar, and other methods. And there are all kinds of sites where you can look at fraudulent science, retractions, that tabulate all those things. So that could be a good place to start. Okay, let's now switch and start our meeting today. Just a minute. Not there yet. Actually, let me stop this share. Get this one.
Simon, I have a question here.
Yes.
Can you hear me? So in this talk, do we need to prepare slides?
Yes. So you're going to give a PowerPoint presentation using Zoom.
Okay.
That's the idea. And you're going also to write. You're going to write 2-page analysis of this paper. So
okay.
Assignment
That's the final assignment, right?
Sorry?
Yeah, okay. That's the final assignment, right? That 2-page analysis of the paper is the final.
Yeah, so that will be a PDF, right? A Word or a PDF. I'm having, here we are. Okay, everybody can see this?
Yes, we can see.
Okay. So the first thing I want to ask you is, how are you doing?
Good.
No, but we have to use many for that. Just wants a warm up because we are going to use Mentimeter to ask other questions. Everybody has costumes? For Hanukkah, Roladin is doing some terrific sufganiyot. What about the Oznei Haman? You're ready with that? Okay. Tired. So most of you don't feel the war? Okay. Why is that doing? Okay. All right. So let me remind you where we finished last time. We talked about the replication crisis, many examples. It's actually really type of a relatively new issue that was really raised in a big way only in 2005. We are in 2022. So it's a basically 2-decade issue that the scientific community is handling this crisis and trying to figure out what to do. And because of this replication crisis or reproducibility crisis, many things have changed. And this is really recent. So we mentioned that this is mostly affected psychology and medicine, but it affects every discipline, really. And we ask what are the causes for the replication crisis. And here is a list. Let me get to the later. So selection bias, generation of new data or publications at an unprecedented rate. There are just too many of us, basically. Majority of these discoveries will not stand the test of time. Failure to adhere to good scientific practice and the desperation to publish or perish. So basically, this addresses the issue of incentives. We are incentivized to publish. This is how we get promoted. In China, for a long time, this is how people got money. You publish science paper, you got a big raise in your salary. So obviously, that's not the right incentive to publish good science. The incentive should be to publish the best science you can. And we are actually struggling with this. It's very hard to build a system where you are promoted based on how good your science is and not the number of publications and the type of journals. And if you really want to do very good science, you should take your time. When I started my scientific career, you would publish one paper a year at best. It would take a long time. And nowadays things have changed drastically and people publish like crazy. And since the invention of Word, Microsoft Word, you can cut and paste and you can generate based on the initial paper you started. You don't plagiarize, but you kind of cut and paste and edit and change the text a little bit. And now you make review papers and this and that. So we generate a lot of papers. And there are many stakeholders with different really stakes. So what was a response for the replication crisis? There is now a new word, a new scientific discipline, which is called meta-science, and we'll cover this in a second. Tackling publication bias with pre-registration of studies, shift to a complex system paradigm, emphasizing replication attempts in teaching, reducing the p-value required to claiming significance of new results, addressing the misinterpretation of p-values. So especially in psychology, but in and medicine as well, people use statistical tools without really understanding how they work. So there was a lot of abuse of statistics, claiming, scientific statistical significance where there was no significance. So obviously you need to train all scientists from all disciplines to have basic skills in statistics. Encouraging larger sample size, basically do all experiments, at least triplicates, generate enough data that you can really do good statistics on, sharing more data in online repositories, funding the replication studies, emphasize triangulation, not just replication. So basically do correlation with other methods, raise the overall standards of method presentation, and open science. What does it mean, open science? It means open access. Basically, you don't need subscription for journals, open raw data, open analysis codes, electronic laboratory notebooks. Basically, give enough information for others to replicate. At least give enough tools for people, let's say, from third world who don't have enough money to repeat your experiment, but they can at least repeat the analysis of your experiment. So they can use your raw data and write their own code and compare and see that you did the analysis correctly. Okay, so one of the responses for this crisis is open science. Let's go a little bit deeper into open science. Leon, you should stop me at some time and read me the chat questions, okay?
Actually, we have a question.
Okay.
Somebody asked, may I ask why it replicates? It's still a
Why?
little low for analyze.
Sorry, can you read slowly again?
Why replicates? It replicates.
Why triplicates? So people are trying to figure out how to solve the replication crisis. So one of the answers is, if you do, when I started my career in solid state physics, you would make one MBE grown sample, do one experiment and publish it. In biology, that doesn't work. You have to repeat the experiment many times, and then you have to build controls and so on. But I argue that also in physics, you need to do that. So the idea is that you repeat the same experiment again, and even just to learn what the error bars are. If you repeat it again and again and again, now you can calculate the mean and the variance, and you have an idea what the error bars is and how confident you are in these results. So this is why to replicate. I mean, part of the answer for the replication crisis is do the experiment many times over and over again. That's one of the answers. I don't necessarily agree or know that this is the best answer. We are still struggling. I want to convey to you the issue of this crisis as an ongoing issue that we are all struggling with. We don't have good solutions as of yet. It's fresh, it's relatively new. Other questions?
The question is basically what was asked in the chat. It was why triplicate? Triplicate sounds really low amount to validate.
Well, I think that really depends on what the details of the experiment, the field, the topic, the subtopic, exactly what the experiment that you do. Some you don't need to replicate many times. Some you do. Depends on the details. But basically, the idea is that you don't do one experiment once and publish. You do an experiment, you do a control, and you repeat it at least 3 times, and you look at the means and the variances and so on. That's a minimum. Of course, you can do much more. More questions? Okay, so let's go to the Wikipedia definition of what open science is. Open science is a movement to make scientific research data and dissemination accessible to all levels of an inquiring society, amateurs or professionals. So not only that you want to solve the replication crisis, but since the public is funding your work, you're actually getting your salary paid from the taxpayer money. Then if a taxpayer money wants to read about your research, that should be available to him. It used to be that only university libraries had access to scientific journals. And if you were part of the university, you had access to these too, but the layman people could not. But the argument is if they pay taxes, they should be able to read your papers. So they don't have subscription, they don't belong to the university. So you need to make papers available to all. That really shifted the whole way of how scientific publishing is done. And unfortunately, the publishers, the scientific publishers like Elsevier and Springer and so on, they all had to shift, and they fought it. They fought it really hard. They did not want to do this because it totally changed their business model. But nowadays, all the scientific publishers have both subscription and open journals, and the scientists can choose which journals to publish where. But they were forced basically to do this. It encompasses practices such as publishing open research, campaigning for open access, encouraging scientists to practice open notebook science, and generally making it easier to publish and communicate scientific knowledge. Hallmarks of open science are open access journal and preprint servers. You can ask Leon or anybody from my group, but most of the people I interact with do this nowadays. You put your paper before it goes to the journal in either bioRxiv or in arXiv. And that makes this immediately accessible and open before the paper went through a peer review. So these are the pillars of what open science is all about: open data, open source, open methodology, open peer review, open access, and open educational resources. And basically, we need to practice all. So whenever we write papers nowadays, we put the raw data in depository. We put the code that we used for data analysis in depositories. We put the paper in bioRxiv. And most people that I know do this. So, and this is a very quick shift that happens over the past decade.
Sorry, can I have a question?
Yes.
In order to publish an article, you have to pay to the journal, right?
Okay, so we are coming here into the business model. It used to be that the library in your university paid subscription fees. And they would, in different universities, more rich universities had more journals available. Poorer universities had fewer journals. But the publisher was really relying on this subscription fees. And individuals could subscribe as well, right? I'm actually subscribed to Science, Nature, or Physical Journal, and so on. So I pay subscription.
Yeah, so people need to pay in order to publish and also need
no, wait a minute,
to open, no?
Just a minute, I'm not finished. I'm trying to answer. So what I'm saying is that the old model was only subscription. That funded the publisher cost to handle the publishing, right? To have the peer review, to have the editors, to really put it into print. That cost a lot of money. And the way they did it is from subscription fees, individuals and libraries. The open science business model is very different. The author who submits the paper pays for that cost. So now it suddenly jumps. You have to pay much more money to publish a paper than you used to. We just recently wrote a review, actually, from Bar-Ilan with Zahavit, and they asked $3,500 for that paper. I fought it because this is outrageous. You know, many journals popped up just for making money because of this shift. So you have to be very careful. There are what we call nowadays predatory journals that are, I don't know, in India or China. The whole purpose is to scout for, scientists who really kind of clueless, and then get them to publish in their journals and then pay. And people just try to make money this way. So that's very dangerous. But the model for the open science is that you pay the cost of the publication. And the better open science journals, which are reputable, the cost is not prohibitive. It's more like $1,500 or $2,000 per paper. Did I answer your question?
Yes,
Okay.
thank you.
Other questions?
May I ask, please?
Yes.
So doesn't this refute the concept of the replication problem, because now the journals have interest to publish more and not necessarily better?
Excellent question. Excellent question. So as I'm emphasizing, we are in transition. We don't have the final solution. And you have to be very careful. So some of the open science journals are terrific. And they are run usually, you know, almost all scientific societies nowadays. So for example, one of the journals we like to publish a lot in is Biophysical Journal. It's still a subscription journal, but they allow individual papers to be open, but those will be more expensive. And this is a scientific society. They don't have basically financial interest. They just want to disseminate biophysical science. So it depends on the detail, and you as scientists need to be a little bit more sophisticated nowadays, recognize which journal is a predatory journal and boycott that journal and just publish in the right journals. And I'm sure these things will sort out over time, but we are in a transition period. All right. So this idea of open science, as I said, is relatively new. There was a lot of discussion in the early 2000s and late 2000s. You could read about it, you know, in Science, Nature, lots of editorials about this. The ERC, the European Funding Agency, stepped down and said, everything we found has to be open science. And then the American funding agencies followed through, NIH, NSF, DOE, DARPA. Nowadays, as a scientist paid by taxpayer money, you need to publish open science. So you can look here. This is basically the policy of the NIH. I'll post the lecture so you can find those links later. Funding agencies accept grantees to publish in open science journals and pay the corresponding fees. Deposit manuscript in repositories. So example for repositories are PubMed Central for NIH, Archive, BioArchive, ChemArchive, and so on. Deposit raw data in repositories like Xanadu, Dryad Digital, Figshare. Deposit analysis codes, GitHub. We put quite a few tools on GitHub ourselves. Disseminate results and make them accessible for all. So, you know, it used to be that scientists were sitting on their ivory tower, talking to themselves, getting money and do whatever they want. And this is changing. It's clear that we have responsibility towards the general public because they fund us to do science correctly and to make it available to all.
Do you have an opinion on websites such as Sci-Hub, which at the end of the day obviously has legality issues, but in a way they're just bypassing...
Well, they try to override the subscription concept. What they do is totally illegal. They take journals which are not open science and put them available to everybody to steal. So yeah, legally, they are not doing the right thing, right? But many people are relying on this, right? So no good answer. And I don't know if ever somebody will manage to bring them to court and shut them down. But, you know, it's the same way as Dara.tv, right?
Yeah, but there they do close them down. Whereas this seems to be...
Well, it's interesting because I watch all the Israeli content through Dara.tv outside of Israel. This is still working, but in Israel, you cannot do this. So same type of, you know, there is an issue of intellectual property that is protected and you're stealing it. What they do is stealing. So obviously it's wrong. There is a better, good motivation, you know, to make it, but a better solution is for everybody to publish open science. Problem is that Science and Nature still have such good name that everybody wants to get such science and nature paper because your promotion is going by how many science and nature papers you have, which is a wrong incentive. So eLife came exactly for that reason. eLife was the first paper started by, I forgot the guy's name, he later got the Nobel Prize from Berkeley. That was the idea. He brought several Nobel laureates around to have the editorial board and say, we are going to have a paper, a journal as good as Science and Nature. We want everybody to publish in our journal, and it's going to be open. So get rid of Science, Nature, publish in eLife. That's the right way of doing it. And make eLife a better paper. Ron?
Yes. Well, I asked in the chat. I'm just trying to understand why is this approach of open everything is necessarily the right approach. I mean, I think it is debatable, specifically when I'm thinking about open peer review. I mean, I don't necessarily see the benefit in open peer review.
Ron, I want to move on, so I'll cut you short and I'll answer quickly, and we'll move on. And if you have more questions later, we'll answer. I think I emphasized several times, we don't know what's right.
Okay.
We're in a transition period. I'm not arguing that open science is the best solution. I'm just telling you what happened in the last 2 decades. And we are in transition and we are experimenting. So when you become, established scientist in 10 or 20 years from now, things might be different. Just accept it that we are in a transition as a response to the replication crisis and as a response to the taxpayer money demands. And we are seeking for the best solution, and I don't know that we have it as of yet.
All right, thank you.
Okay, so we have this open science movement. Other groups must be able to reproduce experiments and the analysis of the existing data for confirmation purposes. Ultimately, if practiced fairly, open science should entice everyone, including commercial vendors, to adopt and contribute to community-defined file formats, provide free file conversion codes, and open their analysis tools for scrutiny by the community. For many years, vendors that sell, let's say, microscopes or all kinds of scientific machines have their own data acquisition software. They have their own file format. It's all closed. You just have to interact with their own software to get some analysis, and you spit out some figures, plots, whatever, that you're using in your publications, but you don't know what inside, what the kishke inside, what the guts inside. That's problematic because you cannot replicate, even if you have the data, you cannot replicate because the vendors kept everything in a closed box. So we have generated many, many codes over the years, specifically for single-modality threat. I'll describe this in 2 meetings from now. We actually wrote code for file conversion, taking raw data from vendors that don't open up stuff and converting it to a file format that everybody can use and do things with it. So it's not only the journals. Think about all the scientific instrument makers that give you a total solution, but you don't really have access to the very raw data or others who want to follow what you've done and try maybe some different analysis. Okay, so this is slowly changing, but the community needs to demand from scientific instrument makers to make their code accessible, open, and not charge money for it. Finally, online and public repositories are a form of data and knowledge backup, which most of us have learned the hard way, and it's difficult to achieve and maintain at the scale of single laboratory. So I cannot tell you how many students I have in my career who lost their data because hard drives fail. We'll go over some pretty amazing fraudulent science cases. And one of the excuses was, I lost the data. So by the mere fact that you are required to put your raw data up in a repository, you are making yet another backup of that data. So obviously, I hope that all of you in all of your labs have, more than one hard drive where you're in a cloud backup and hard drive backup and a third place backup. And putting stuff in a repository is another form of backup. Okay, so let's ask, what are the advantages of open science? Okay, I think we got enough response, making it accessible to all, transparency, inspiring, free, less mistakes, everybody can read. Okay, good. Oh, wait. I'm having difficulties switching between those two different things for some reason. Okay. So we were talking about advantages. So you all gave really good inputs. Open access publication of research reports and data allows for rigorous peer review. It's not only the peer review itself, but once it's all open, people in social media, and nowadays every scientist have a Twitter account, except for me, or Instagram or whatever, and you can start to have discussion about the paper after it was published, after it went through peer review, and you basically get all kinds of comments. And it's a live peer review that is ongoing. Publicly funded science is publicly available. So a very, very good example of this is COVID. The minute COVID started, all subscription journals, including Science and Nature, came together and announced that any paper submitted to their journal that has to do with COVID is open science for free. No subscription. So that was an immediate response. It happened in real time, and science was publicly available even for subscription journals, because obviously the idea was to save humanity and get vaccines and treatments up and running very quickly. Open science makes science more reproducible and transparent. That's a hope. We don't have a proof for that as of yet. Open science has more impact. That's also questionable. Open science helps answer uniquely complex questions.
Why more so than non-open science?
Sorry again?
Why does open science help unique questions that until now non-open science?
That's a presumption. We don't have proof for any of that as of yet. It's all new. All right, so we asked for advantages. What are the disadvantages? A lot of information. Atakot, copying. Well, nowadays we have pretty good tools for plagiarism, and I think most when you submit something, they run through those AI filters for plagiarism. So I'm not sure that this is a big problem anymore. Prior art, well, intellectual property, talk about this. Publish faster than you, less funds. Full data spread faster. Quantity over quality. Copyrights. Yeah, so again, I emphasize we don't have all the answers. We're running a huge experiment right now, and it's all new. Okay, so the disadvantage are potential misuse. The public may misunderstand science data. Oh boy, we had so much fake news and wrong interpretation of science related to COVID. Some innocent scientists publish quickly something because COVID is very important, and immediately the journalists and whoever start to put, a different twist and different story around this. And there was so much misinformation about COVID because of open science. So on one hand, you immediately started to get scientific answers about the virus. On the other hand, you had a lot of misinformation. So the structure of the spike protein came out like within a few weeks. And then structures of all the important enzymes within the virus and so on. And that was fantastic. And it was immediately all available. In fact, my group here at UCLA, we immediately started to work on transcription with the RDRP, the polymerase of the virus, because it was immediately available. You could ask people to send you plasmids. That was fantastic. On the other hand, there was so much misinformation. Just somebody published something and immediately tons of experts, right? Interviewed on TV, come up with all kinds of explanations and really misusing this open science data and telling the public the wrong thing. Low quality science, you publish everything because you have so many journals and some of them are really low quality and they're just to make money. Entrapment by platform capitalism. So some of the big guys can kind of take over and okay, so now you do open science just with Springer because they build the best platform and whatever. And eventually somehow they find a business model to make money off this. And possible missed opportunity for intellectual property. There is an immediate tension between writing a patent and protecting whatever you've done versus making it public and available for everybody immediately. So this tension is not resolved, and obviously, if you have something that you want to protect, you cannot publish it as open science. You first need to file a patent. Okay, so we talked about the first response was to the publication crisis was open science. We talked about advantages, we talked about disadvantages. But for the good or the bad of it, it's here with us to stay. All the funding agencies adopted this and they require it. Journals have adopted it and it's here. So we are running this huge, gigantic experiment, but we think that the open science will improve the way we do science. That's basically the hypothesis here. So this is a paper from a year ago, January 21, in Science, and basically it's a featured article. Open access takes flight. So it's here to stay. This is like 10 years after it started, and I would say, look, most of the journals are doing it, most of the funding agencies are doing it. It's here. Yes, there was a question?
Yes, there is a question from the chat.
Yeah.
Why there is a misinformation if the papers are peer-reviewed? Why there is a misinformation with open science if the papers were peer-reviewed?
Well, is peer review does what it's supposed to do? Can peer review prevent, mistakes to happen or wrong interpretation to happen? We'll ask that question. We actually have a few slides on this. So peer review is not an answer for everything either. Open science is not, and peer review is not. Other questions?
No.
Okay, so there was a crisis. The first response is open science, and now what's beyond? So people realize very quickly that open science is not the only response or enough response, and you have to go beyond this. So this is just a paper from Nature Physics, 2019. Open is not enough. And this is about particle physics. There's a solution adopted by the high energy physics community to foster reproducible research are examples of best practices that could be embraced more widely. The first experience suggests that reproducibility requires going beyond openness. Oh, these guys have pretty good self-esteem, and they think that. So I like this reproducible research. No, here, example of best practices that could be embraced more widely. We do it right, and everybody should adopt what we are doing. That's basically what they're saying. So this is a figure from this paper, and so they do all these collisions in the accelerator, collect all the data, deposit it, make it open, and put it in archive, and okay. And, so somebody, I think, asked last time, what are the issues of reproducibility in physics? So this is one area where you actually do have issues of reproducibility. In fact, there is a famous case, somebody can pick it up, of finding new elements in Berkeley's accelerator where things were not reproducible, really, and the interpretation was wrong. Okay, so what's going beyond open science? Now we have a term for this. It's called meta-science. It's a new discipline. Meta-science, also known as meta-research or evidence-based research, is the use of the scientific methodology to study science itself. Meta-science seeks to increase the quality of science research while reducing waste. What does it mean, waste? A lot of papers that could not be reproduced cost a lot of money for the taxpayer. Reagents, salaries, whatever. You do a lot of work, and eventually you figure out that all these results don't worth much. So the idea is to make science more reproducible, throw away the bad science, keep only the good science, and basically use science itself to improve how we do science. It's also known as research on research and the science of science, as it uses research methods to study how research is done and where improvement can be. So we had questions earlier about peer review and about open science. So now you can formulate hypotheses and ask and do some kind of an experiment or some, at least statistical analysis. And ask, is open science effective or not? Is the peer review as we know it effective or not? And try to argue using the scientific method, what would be the best review process for a paper, or what would be the best open science practice. Meta-science concerns itself with the field of research and has been described as a bird's eye view of science. In the words of John Ioannidis, science is the best thing that has happened to human beings, but we can do it better. So he was the first to cry, the king is naked. But still, we know that science has advanced human life so much, especially in the last 200-300 years. And in general, science is working. We send people to the moon and maybe to Mars soon. And we build A-bombs and we do all kinds, and Putin has this supersonic missiles at 5 Mach. So we know how to do things better because of science. And we really, most people on Earth are not hungry anymore. That's going to change because we are running out of resources. But we have this population explosion on Earth because we have antibiotics and we have sewer, and so we really solved a lot of problems with science. But we recognize that some issues and we can do science better. And the replication crisis was some kind of a alarm call that maybe we should change things and do things even better. So meta-science actually is not something new, but it took a different twist and new direction after the replication crisis was kind of recognized and introduced. So already in 1966, an early meta-research paper examined the statistical method of 295 papers published in 10 high-profile medical journals. It found that in almost 73% of the reports read, conclusions were drawn when the justification for this conclusion was invalid. So already in 1966, there is a paper saying, guys, you don't know statistics. You're using p-values wrong in medicine. In 2005, John Ioannidis published a paper titled Why Most Published Research Findings Are False. We have seen that title, which argued that a majority of papers in the medical field produce conclusions that are wrong. The paper went to become the most downloaded paper in the public library of science and is considered foundational to the field of meta-science. Later, meta-research identified widespread difficulty in replicating results in many scientific fields, including psychology and medicine. This problem was termed the replication crisis. Meta-science has grown as a reaction to the replication crisis and to concerns about waste in research. Many prominent publishers are interested in meta-research and in improving the quality of their publications. So there was a question about peer review. Science, Lancet, Nature, they recognize those issues. And in fact, you will find very often, if you follow the editorials, every now and then they will have something about open science, something about meta-science, something about peer review. They are interested in getting better peer review, such that, sometimes there are retractions for Science and Nature papers. They want to minimize those retractions. They want to publish only good papers that will stand the test of time. But currently they don't. So somehow the peer review misses, and every now and then you have papers that need to be retracted. So can we use science to learn how to do the peer review better, the open science better? So we talked about the reproducibility initiative for cancer. It was launched by +ONE in 2012. It was just concluded December 2021, and the results were miserable. In 2015, Biomed Central introduced a minimum standards of reporting checklist for titles. So basically now journals come up with a list of things you need to do when you submit a paper. We just recently submitted a paper from a group at UCLA to communication biology, and I've never seen anything like that before. Just to be able to submit a paper, you need about a week of submission work. They had so much details about how to do things. Especially in biology, they want to make sure that you have all the controls and all the data. If you are doing DNA sequencing or any of the common biological assays, you have to give so much detail. So this is a response. The first international conference in the broad area of meta-research was the research waste or equator, and we'll go through this acronym in a later slide, conference held in Edinburgh in 2015. So it's a new discipline. It has a new journal. I'm not sure if it has a society as of yet, but there is already a conference, yearly annual conference on meta-science. The first international conference on peer review was Peer Review Congress. That was even before the replication crisis was brought into focus. This was in 1989. Already then, there was the recognition that the peer review has flaws and we might need to improve peer review. And in 2016, the journal Research Integrity and Peer Review was launched. So now you can publish papers about how good peer review is. And you can do experiments and do some statistical analysis and publish a paper about peer review. The journal's opening editorial called for research that will increase our understanding and suggest potential solutions to issues related to peer review, study reporting, and research and publication ethics. So meta-science can categorize into 5 major areas of interest: methods, reporting, reproducibility, evaluation, and incentives. So methods. Meta-science seeks to identify poor research practices, including biases in research, poor study design, abuse of statistics, and to find methods to reduce these practices. Meta-research has identified numerous biases in scientific literature. Of particular note is the widespread misuse of p-values and abuse of statistical significance. Reporting. Meta-research has identified poor practices in reporting, explaining, disseminating, and popularizing research, particularly within the social and health sciences. Poor reporting makes it difficult to accurately interpret the results of scientific studies, to replicate studies, and to identify biases and conflicts of interest in the authors. Solutions include the implementation of reporting standards and greater transparency in scientific studies, including better requirements for disclosure of conflict of interest. It used to be that if you were on the scientific advisory board of a pharmaceutical company, you would write a paper, you did not need to say that you are part of that company. So that created a lot of issues in terms of conflict of interest. So now you are required to report any conflict of interest. There is an attempt to standardize reporting of data and methodology through the creation of guidelines by reporting agencies such as Consult and Equator networks. So this is just what I mentioned about communication biology. I was really surprised to see the level of details they require in terms of reporting. That makes our lives much more difficult. But this is a response because we cannot replicate each other's results. So maybe we do need to go through all this extra pain and it will take us a week to submit the paper. I don't know, but this is at least what is currently being done. Reproducibility, I'm not going to cover this because we covered this last time. Evaluation, meta-science seeks to create a scientific foundation for peer review. Meta-research evaluates peer review systems, including pre-publication peer review, post-publication peer review, and open peer review. It also seeks to develop better research funding criteria. There was a question about peer review. Is open peer review good or not? So we talked about this a little bit last time. You can have double blind, single blind, or totally open. You can have peer review pre-publication or peer review post-publication. Some of the people say, let's the scientific community judge. We don't really need peer review. Put everything out there and time will tell. And social peer review will basically eventually over time give you a correct evaluation of the paper. I don't know. No answers. Still open. When we'll cover Watson and Crick next week, there was no peer review at that time. Can you imagine? The editors would decide, or at best, he would ask somebody just to read and give him some opinion. There was no written peer review. We had few journals, few people, much fewer rate of submission papers, and the editors could do the work. And they were not experts in all the fields. So things have evolved and changed over the past 50 years a lot. And today we come and say clearly, we don't know what is the best way to evaluate the quality of a paper. And maybe we need to build some research guidelines that eventually will tell us, what is the best way of doing it. And it might be discipline dependent and many other different factors. Incentives. Meta-science seeks to promote better research through better incentive system. This includes studying the accuracy, effectiveness, cost, and benefits different approaches to ranking and evaluating research and those who perform it. So you are all probably familiar with the H factor and a few other measures, and this is one way of looking at things, and some people have lots of criticism about this, and how many Science and Nature paper you have, and are you going to be promoted to tenure or to full professor because you published in the past 3 years, 3 science papers? Those are very difficult questions, and meta-science looks to answer, should we change the whole incentive system to make sure that we publish good science rather than crappy science? Critics argue that perverse incentives have created publish or perish environment in academia, which promotes the production of junk science, low quality research, and false positives. And I would argue incentive to be crooks. And we'll talk about that a lot. According to Brian Nosek, the problem that we face is that the incentive system is focused almost entirely on getting research published, rather than on getting research right. And that's possibly the biggest issue. We somehow need to change the incentive system that everybody will be motivated to do research right. Publish less, but whatever you publish, make sure it's the best science that can be done. Nobody knows how to do this. And I sit on a lot of promotion committees, and it's not resolved. We still look at the number of publications and the quality, the journals and so on, and there is no good answer as of yet. I don't know if we'll ever get to a good answer. Proponents of reform seek to structure the incentive system to favor higher quality results. Meta-research identifying flaws in scientific practice has inspired reforms in science. These reforms seek to address and fix problems in scientific practice which lead to low quality or inefficient research. So one of the solutions, we mentioned this briefly last time, pre-registration, the practice of registering a scientific study before it's conducted is called pre-registration. It arose as a means to address the replication crisis. Pre-registration required the submission of a registered report, which is then accepted for publication or rejected by journal based on theoretical justification, experimental design, and the proposed statistical analysis. So basically you submit, I'm going to study XYZ, I'm going to use this method, I'm going to use this statistics, and then the peer reviewer will say yes, no. If you got yes, you don't go through a peer review again. When the experiment is completed, you just submit the results. So this is one thought that could solve the problem. I'm not sure. Peer registration of studies serves to prevent publication bias, reduce data dredging, and increase replicability. So we talked about reporting. Studies showing poor consistency and quality of reporting have demonstrated the need for reporting standards and guidelines in science, which has led to the rise of organizations that produce such standards, such as Consort, Consolidated Standards of Reporting Trials, and Equator networks. Equator, Enhancing the Quality and Transparency of Health Research Network, is an international initiative aimed at promoting transparent and accurate reporting of health research studies to enhance the value of reliability of medical research literature. So now there are organizations that require how to submit data, analysis, papers, all the reporting standards. And I mentioned to you my own recent experience with communication biology, and their reporting requirements are really extensive. The Equator network was established with the goals of raising awareness of the importance of good reporting of research, assisting in the development, dissemination, and implementation of reporting guidelines for different types of study design, monitoring the status of the quality of reporting of research studies in the health science literature, and conducting research relating to issues that impact the quality of reporting of health research studies. The network acts as an umbrella organization bringing together developers of reporting guidelines, medical journal editors and peer reviewers, research funding bodies, and other key stakeholders with a mutual interest in improving the quality of research publication and research itself. Okay, so we basically finished the topic of meta-science. Any questions here? Anything on the chat, Leon?
No.
Okay. All right, so let me start a new topic, which is how to write or to critically read a paper. Write, obviously, good paper. Read, I don't know, it depends what you get. But how do you critically read it? So this is very highly important for future and success of scientists like yourself. Being able to write a good paper is very important. You can have the same results published and written in a very clear and logical way and have a large impact, or you can write it in an obscure way and this paper will not be cited. And although it has the right important result, it's not written well enough. You don't communicate your ideas and excitement and results well enough, then the impact is lower. So having some guidelines how to write good papers is very important. And when you are assigned to read a paper in this class, how to evaluate a paper if it's good or not is very important, because you will soon start to review other people's work and submit your peer review to journals that ask you to do so. As scientists, we are expected to not only hypothesize, conceive, perform experiments, and come up with theories and explanations that push forward the front of knowledge, but we also need to sell our merchandise. So part of what we do is really becoming salesmen. You've done some work, and now you want to convey whatever you learned to the scientific community, and you want to be effective at this. So this is nothing but becoming a salesman. There are different ways of how you sell your merchandise, and selling scientific merchandise is basically publishing good papers in good journals and going to conferences and presenting good presentations in the conferences. It takes skill it takes experience, and you're all going to be required to present for 25 minutes. And that's part of the training. So it's very important to know how to convey the information in a way that is engaging, convincing, capturing the audience. So in fact, at the end of the day, you are being promoted partly based on your salesmanship skills. This is maybe shocking, but you know, two individual researchers with, let's say, identical scientific results, but different salesmanship skills, guess who will get the job when they both come to an interview? One guy gave a very captivating talk, so the faculty is going to decide if he's going to be hired or not. And one was kind of boring in presenting the same work. Who will be hired? What is a good paper? And how to write a good paper? Success at publishing is used to evaluate scientists and can help predict their future success. And as we said a few times already, that might be the wrong incentive, but this is the incentive that is ongoing. We have not changed that. You still need to publish, and publish a lot, and publish in good journals to get promoted. So you better learn how to do this well. So the idea of concept transfer, that's basically you study something, you build a concept, you have an explanation, and now you want to communicate this to the scientific community. Concept transfer is the rate limiting step in the scientific endeavor. And learning how to do this well is very, very important for your future. Bad salesmanship skills bring about problems in replication, retraction, photomath science. So what do you think are the ingredients for writing a good paper? Clear language, grammar, simplicity, order, comprehensive explanation, enthusiasm, something to say, specific data, clear data results. All right, great, thank you. So this is obviously a very popular topic, and there are endless resources. I'm again going to give you a list of links that you're invited to have a look at. Many people have something to say about this, how to write a good paper, right? There are many different opinions and no one answer fits all. So I'm giving here a list of some recent references. This is actually from Nature in 2018. They interviewed several very successful scientists, and they asked them what they think are most important ingredients in writing good papers. So that's an interesting read. This is actually a publisher, Elsevier. They asked Borja to write. He wrote basically a series of 3 papers. 6 things to do before writing your manuscript, 11 steps to structuring a science paper, writing a science paper, some do's and don'ts. This is from PLOS Computational Biology, Trends in Ecology and Evolution. The whole book. This is an SPIE book on how to write a paper. And this is, you know, you can hire for money people who will take your draft manuscript and try to improve it. So this is an editing company. It's a commercial company that makes money for people who are not sure about their writing skills, and they can basically improve the paper. They also have a guide, since that's what they do for a living. So there are many, many resources. I'll put the PowerPoint slides on Moodle, and you can look at those resources, how to write a good paper. What are the principles? So rule number 1, focus your paper on a central contribution which you communicate in the title. Basically, the paper should be about one story. Don't mix several different stories in one paper. That never comes well at the end. Rule number 2, write to flesh and blood human beings who do not know your work. Oftentimes we try to write papers to ourselves or to people who are very similar to us, but you want to somehow appeal to a larger audience. So you need to write it in without too much jargon and with a language that will appeal for everybody. Stick to the context, content, conclusion scheme, and we'll talk about this later. Optimize your logical flow by avoiding zigzag and using parallelism. So this is, in my view, one of the most important rules. When you write, first of all, you write one story. Second, you build a logical tower that is very strong. You cannot break the walls of that tower because the logic flows from one point that you make to the next point that you make to the third point. The figures follow that logic, and they all assist you in telling that one story, and you cannot break that logic. That's very important in order to write the paper well. What are the components? Tell a complete story in the abstract. So the abstract really need to be a very short version of the whole paper. Communicate why the paper matters in the introduction. So you give an introduction, you basically say there is a lack of, this is what we know about this topic, but there is a lack of information here, here, and here, and my paper addresses this one particular deficiency, and this is why it's important. Deliver the results as a sequence of statements supported by figures that connect logically to support the central contribution. Discuss how the gap was filled. So basically there was some gap in information and you filled it. What are the limitations of your interpretation and the relevance to the field? So you always want to put some qualifiers and say, well, I did this, but still we are not absolutely sure about this. This is the topic of a future investigation, and this is why it's relevant. So we talked about principles, components, now the process. Allocate time where it matters, title, abstract, figures, and outlines. So it's very important to have a very precise, to-the-point title, abstract as well, then build the figures, then the outline, and then you can tell the story. Get feedback to reduce, reuse, and recycle the story. So here is a table that shows rules and what happens if you don't follow those rules. So rule number 1, focus on the big idea. If you don't do that, readers cannot give one-sentence summary. Basically, when a reader read a paper and somebody asks him, what did this paper really tell you? What is left after you read this paper? You need to get that one big idea. If you didn't get it, obviously the paper is not good. Write for naive humans. If you don't do that, readers do not get the paper. So if it goes beyond you because language is too sophisticated, concept are too sophisticated, it's not written for everybody. Use this concept that we talked about, context, content, conclusion, structure. Again, that will be the next slide. Readers ask why something matters or what it means. So basically, they didn't really get it. Optimize logical flow. Readers stumble on small section of the text. Abstract, compact summary of the paper. If you don't do that, readers cannot give the elevator pitch of your work after reading it. Introduction, why the paper matters. If you don't do that, readers show little interest in the paper. Result section, why the conclusion is justified. If you don't do that, readers do not agree with your conclusion. Discussion after the results. Preempt criticism, give future impact. Readers are left with unanswered criticism and or questions in their mind. Allocate time wisely. Readers struggle to understand your central contribution despite you having worked hard. Iterate the story. You want to tell the story in the abstract. You want to tell the story at the end of the introduction. You want to tell the story in the conclusions. The paper contribution is rejected by test readers, editors, or reviewers if you really do not drive through the message. Okay, so let's talk about this concepts of content. How did we call this here? Context, content, and conclusion. So this is color-coded. Summary of a paper's structural elements at 3 spatial scales, across sections, across paragraphs, and within paragraphs. Note that the abstract is special in that it contains all 3 elements of context, content, and conclusion, thus comprising all 3 colors. So this is the abstract. The abstract, we are going to say, this is a question, this is how we do it, and this is why it matters. So you see there is some color coding, and this color coding is kept here. Introduction is really about what is the question and why is it important. So what is a big problem in science that defines the field domain, narrow problem within, and yet narrow paper gap, and what exactly you are addressing, what the field knows, remaining gap, our approach. So that's the last part of the introduction. You put a small summary and say, this is what we do, this is why we did it. The introduction explains why there is a gap, this is how we do it, and we got these results, okay? And you repeat this again in the conclusion. Then you have the main part of the paper, which is the results. You go over the methods and how we address it, and then you build this logical flow that we discussed. And the last part, the discussion, you basically present the results with your analysis and conclusion. We found that, we filled the gap of. What are the limitations or our limitations, and how to interpret, and what additional experiments need to be done after our own. What did we contribute? What is the strength of the paper? What it is useful for, and the difference made. So this is kind of a very generic, but I think it's true for all papers. You want to lay it out in this structure. And this is very dry, right? Personal style often leads writers to deviate from a rigid, conserved structure, and it can be a delight to read a paper that creatively bends the rules. However, as with many other things in life, a thorough mastery of the standard rules is necessary to successfully bend them. It's very dangerous to write a scientific paper not according to the rules. And basically the claim is here, only if you know the rules very well and you've used them in the past, you can try to play with changing the rules, because usually it doesn't work well. On the other hand, writers must be careful about creativity. It sounds good, but the purpose of a scientific paper is to convey information. That's it. Flourishes can be distracting. Figurative language can also bamboozle a non-native English speaker. My advice is to make the writing only as complex as it needs to be. So this is really about the conventional way of doing things, and we gave an example. It has to be accurate, non-emotional, strictly relevant, formal, objective, impersonal, clear, linear, and concise. If you don't do this, it's inaccessible and it's not accurate. Counterculture is being smart ass and, trying to do things different, write an entertaining paper. It still concise, but you try to be sensationalist, oversimplify and hyperbolic, and that's very dangerous. So basically, the idea here is to find some kind of a yin and yang combination of these two, where you have the right structure and your linear flow and logical flow and so on, but you're trying to be a little bit more inspiring. So how to evaluate quality of writing on impact? There have been no in-depth studies linking writing quality to impact, but here's one example. Healthcare articles with simple and declarative titles were more likely to be in the Altameritic top 100. I'm not sure what that is. It's some kind of rating of papers, health-related papers. But this title already tells you this is a meta-science research. They analyze papers by their titles, and they have some statistical analysis and trying to figure out if better titles have more impact than not so well written titles. So again, meta-science is the new field that is formed that will look into what do we really mean when we say this is a good article and this is not. Can we be more quantitative? Can we give better rules on how to write a good paper? Okay, let me just finish quickly for today with repeating what the analysis, what is the requirement for you to do in this course. Excuse me. So as I told you several times already, I want you to tell us a story, and I want you to tell us a good story. You're going to write a 2-page critical analysis of the paper of your choosing, and you're going to present this in a PowerPoint 25 minutes presentation. The choice of papers, there can be many different papers, so you can choose a seminal paper, but then I want you really to do good work in trying to explain why this became such an important paper. This one is taken, by the way. I'm covering it next week. It can be an excellent recent paper, but it's very new. So how do we know that it's going to be really impactful? What is the initial citation? What is the rate of citations? Why? An example of a bad paper. And here we have many examples. It could be just errors, innocent errors, it can be mistakes, using the wrong interpretation, the wrong methods, the wrong theory, or it can be non-reproducible. We talked a lot about reproducibility and why. It can be an example of famous fraudulent paper, an example of a retracted paper. What were the reasons? Or an example of a famous erratum. This is basically publishing a correction to a paper. So when you find such a paper, we want you to follow the following rules. Do the authors state the problem clearly? So that's basically the introduction. Do the authors give a good historical overview of the problem? Do the authors explain well their hypothesis? Do the author explain well their approach and methods, or in case of theory or experiments? Do the authors explain well statistical analysis? Do the author explain well their novel contribution towards solving the problem? Do the author perform adequate control experiments? Do the author explain well what was learned? How did they move the field forward? Then find the list of other papers that are crucial for understanding this paper. You basically want to go both backwards. So from the point of this publication, go back and see what was already known, what are the key papers that this particular paper you're looking at is citing. And you want to show the impact, what happened after. So for all the papers, find and list subsequent follow-up papers. how many times was the paper cited? What was, respectively, what was the long-term impact of this paper? Nowadays, with Google Scholar tools, you can really look at even graphs of citations over time and see what was the impact of the paper. Were there any problems in reproducibility discovered much later? Any errors found? Was an erratum published? Or were there a retraction? And if you choose to cover actually a more recent paper, then for these last two, we have a little bit different questions. Since it's new, did the authors follow the open access rules? Was it published in an open access journal? Did they provide the open raw data in one of the repositories? Did they provide the analysis codes on one of the repositories for analysis codes? Did they post their electronic notebooks? Is there enough information for application? Since you don't have too many citations, but maybe you have several, and you can look at the slope and you compare the rate of citations because it's relatively new. Okay, so what I want you to do for next week is to read Watson and Crick and Forster papers. They are both posted on Moodle. And I'm happy to answer any questions. Leon, anything on the chat? Okay, everybody's tired? Okay, so let me just tell you what we are going to do next week. I'm going to cover Watson and Crick, and I'm not doing my own analysis. I'm actually going to use an interesting analysis of that paper, and we'll start to touch on energy transfer. The week after, I'll talk about my own research, which is related to energy transfer. And my last presentation would be about fraudulent science and beyond. If no more questions for tonight, I ask you to go back to this Google Sheets, put in your date, and put a DOI for your paper of selection, and make sure that nobody else is doing that paper. Okay?
Till when we can choose a paper?
Sorry?
Like to put, till when can we choose?
Oh, you want a deadline for this? Yeah. Well, I think it's, I'm not going to put a deadline because your interest is to do this relatively quickly because, the good stories are going to run out. So, I mean, there are plenty of, you are around 30 people. I'm sure that you can find 30 good stories about, papers, but some of the stories are so well known and you'll start to search and find, and then you'll ask, can I do this? And somebody already picked it up. So the sooner you put in your own choice, nobody else can touch it, right? So that's the incentive to do it quickly. But if you are busy and you have all kinds of other obligations, do it at your own time. But obviously it has to be done, I would say, within a month or so. Not more than that.
I have a doubt.
Again?
I have some question. Like, I didn't understand exactly what is the history. What is this history? Like, it's the history. I really didn't understand. Like, I don't need to create a history for the article. Like, I see the article.
No.
What is?
So you'll see next time when I talk about Watson and Crick, I will mention what they knew when they started to attack this issue of the structure of double-helix DNA. So there were some key papers that they were aware of, and that was their starting point. So, some papers use very little based on previous knowledge, then you don't need to cover this at all. But some papers do. So you just want to mention, well, when they published this paper, they knew, before they started, they knew the key results in this field until then were this, this, and this, and they addressed this open gap in what was known. That's the extent of what we are asking here. Any other questions?
Yeah, I have a question. Can the story go beyond the scope of the paper? For example, if there's like a...
Yeah. So I got this question already several times. So I'm going to give you a story about a guy who wrote 33 papers. I'll give you one paper of his to read, but then the story gets much bigger. And there are many such examples. But once you identify a paper and a PI, a scientist, put the DOI for the paper and put the name of the scientist, that we won't have somebody else choose another paper from the same scientist. Okay. So that will be eventually a repetition.
Can we use moderate humor for converting a point in our presentation? Because some stories might sound ridiculous to the person who knows the field better. So should we respectfully make jokes, or we should avoid it?
The purpose of this course is to get entertained.
Okay.
and hopefully learn something about how to become better scientists, better writers, understand what mistakes, where they can take you. Don't repeat other people's mistakes, although usually it's very hard. You learn by doing the mistakes yourself. But I hope I bring some value to the discussion. I guess you were not fully aware of the transition, the problems in the transition. I think it's an interesting topic to discuss. I'm going to give you, exciting stories. I want you to entertain. Yes, absolutely. Not me, the rest of you. So, but it has to be based on a real scientific paper that was peer-reviewed and published, and give a real analysis. I just gave you the rules of how to analyze a paper. So it has to have that, but then make it as entertaining as you want. It's, this course is different than the rest of the courses you're taking. Sit down, relax, enjoy. It's a fun ride. Anything else?
About the
Sorry?
incentive. I wanted to ask about the incentive.
Yes.
If it's okay.
Sure.
You think it might change? You were speaking about the incentive for publication, and in my field, medical field, it's I think it's lowest as you can get.
Right.
Published for publication, only number matters.
It's a very, very difficult concept to change, and everybody's struggling with this. But for several hundreds of years, the academia, the whole scientific endeavor is built on promotions based on publications. This is not something you can change overnight. So I think it's with us for many, many more decades to go. But at least we are a little bit more aware of this nowadays than we used to be. So suddenly all kinds of other criteria are popping up. Here in the US, a huge deal is about open opportunities and affirmative action and openness to the other and all kinds of stuff. So suddenly, it's not about scientific excellence anymore. It's about other things as well. Personally, I don't think that's right. I think that ultimately what we need to do is make sure we do the best science we can. And then be open for everybody. But the most important criteria is the quality of science. But some political agendas kind of meddle with this and when China was open to the West and they decided to build their own science, and same with India and so on, it went crazy. There were just, people wrote fraudulent papers and just submitted and copied and lots of plagiarism. And they were not only that they were incentivized to get promoted, but they got money. So it was a money business to publish a lot of papers. So now they're putting some kind of hold to this, and things are changing in China. We always think that science is pure and perfect, and look at it. Yes, they are very impressive, but there are lots of problems, and the question is, can we improve? So this is what this course is about. And I want you as young scientists to be aware of those issues when you get promoted and move forward in the academic ladder, and just be careful and think about those issues. I think those are very important questions. We don't have answers. We struggle with them. We'll continue to struggle with them. But at least we are aware of them. That's already part of the solution. Okay. So, Chag Sameach, happy holiday for everybody. I'll see you next week. And I'll post those 2 papers towards the weekend. Please use the weekend to read the papers and come prepared for the next class, okay?
Thank you, Simon.
Bye-bye, everybody.
Bye.
Thank you.
Bye-bye.